right? So things, what mistake was made, right? Or person A says this, or did this in their research. Person B did this, right? Person A says the variance of the sample is this. Person B says the variance is this. Who's right? Why? Well, what does that require you understand? Requires you understand how you calculate variance of a sample differently from a population, right? So it's always an application level concept. You know, I love my compare and contrast questions. We do them in class. A lot of interpret, which we'll talk about that word in a second. A researcher finds this. Can they be right? Why or why not? Under what circumstance could this be true? Right? You find this. When is that possible? So this is what I mean by conceptual question. You'll notice it's not what is standard error. It's never going to be a question that there will be nothing ever on a test stat of mine, because in real life research, that isn't helpful, right? This is the being able to figure out why something happens is what's helpful, right? And these are the kinds of questions designed. A computational or a calculation problem requires you to use actual mathematical procedures to do something. I bet you right now, if I ask you what computational problems are going to be on this exam, you can tell me. Tell me. Great, Z transformations or t-tests are kind of, sure, if you're hypothesis testing, you could think of that sort of procedurally. What else?
Central tendencies.
That's not computational. Oh, if I said compute the mean, that would be a really boring question, but I could ask you to compute the mean. Go with that Z transformation for a second. What other computational things have we done with Z's? Probability, find the probability of a score above, find the probability between. Look, you already know 4 of the question. Those are predictable, right? We've only done a very specific subset of computational problems, mostly because computational problems are usually prerequisites for theoretical concepts, right? They themselves are not useful. So you teach them as a way of understanding certain concepts, but then we get past them very quickly. So if you're thinking about, you could probably make yourself a list and then stop computing stuff, because that's not going to help you do well on the exam. Clarifying some important exam terms. 2 terms in particular, the word interpret and the word in context. You will see these 2 words in the exam, and you've heard me use them in class, but this is something where students always make mistakes on the exam. And so I wanted, this is the first year where I've explicitly clarified so that people don't lose, people don't lose unnecessary points on this. Interpret. So let's look at this study for a second. A 1 sample t-test was conducted to determine whether Verizon customers, you know the study, service complaints resolution time differed from industry standard. Verizon complaints took significantly longer to resolve than industry standards. T of degrees of freedom 49 equals 2.32, P equals 0.024, D equals 0.33. Now, very common question you will see, right? Why do I ask these? Because that is what you do as a researcher, right? You look at your values and you interpret them. What does it mean to interpret? Well, what is an interpreter? Someone who translates from one language to another, right? That is what it means to interpret, right? A lot of times when people see interpret the p-value in the context of the research study, they say it is significant, right? That's correct, but that's a conclusion, right? Interpret means translate from one language, number, to another language, English. So when we're interpreting P, that's assuming the null hypothesis is true, the probability of getting this value or something more extreme is 0.024, right? Now, that's interpretation, but it's not in the context of the study. Right? In the context of the study, Christina, the lovely Christina edited all the typos and things on the exam, and she added a beautiful reminder, which was in the context means use the names of the variables and the results you obtained, right? That's what it means to put something in context, right? So assuming Verizon resolves complaints on par with industry standards. What is that? Well, what is it? It's the null, right? Assuming there's no difference between the Verizon sample and industry standards. The probability of a sample of Verizon complaints taking 22.3 minutes, that's your result, or something more extreme is 0.024, right? So you have 3 examples here: interpret the p-value, interpret the t-stat, and interpret the effect size, all in the context. Cool. We're gonna go through all these, but this is more high-level exam, FYI. Rounding. A couple people asked about rounding. Just giving you a really simple chart here. So the first thing is, when calculating, someone was like, how many digits do I need to leave it out to when I'm doing the math on my calculator? And I don't know, as many as you feel the brain can handle, right? So when you're calculating, keep them as long as possible without losing your mind. That's my guidance. So if you're doing it by hand, probably, I don't know, I wouldn't want to do more than 4 on paper. If you're doing it on a calculator, you probably can do all 8, right? Because you can keep whatever values in your calculator. But what I really care about more than that is your final answer, right? Because that's the only thing that APA really governs. So there are 2 rounding decisions that you have to make when you're giving a final answer. The first is, how many digits should I follow after the decimal place? And the second is, should I include a leading 0? So when I'm deciding whether to put 3 digits after the decimal place or 2 digits after the decimal place, it's pretty simple. Probability is the only thing that gets 3 digits. Everything else under the sun in stats gets 2, because we care about the specificity of probability. You can think about why. What's our cutoff region for probability? Right, 0.05, right? So knowing whether something is 0.049 or 0.051 matters. That's why probability gets rounded to 3. Everything else is 2. What's that noise? Oh, it's my child, right? The second decision is, do I include a leading 0 before the decimal point, regardless of whether I'm rounding, right, to 3 or 2? The answer is, well, if the value can be more than 1, then you put a 0 in front. If the value can't be more than 1, you don't put a 0, which means, are you ever going to have this, ever? No, because probability can never be more than 1. So whenever we have a 3-digit, a p-value, it's never going to have a leading 0. V.
What if you 0.050 to give it 0.05?
But nope. Your obtained probability needs to be 3 digits. So if you get a value like this, that's not in APA. You need to add this, but not that far away. You need to add the 0. 2 digits is 2 digits. It doesn't matter if it's a 0.
But the alpha can be.
Guys, this is not the most important thing about stats. I promise. If you lose a point for rounding, it's going to be 0.10. Okay, cool. Let's keep going. You can look back at the slide later, but you're not going to be happy if we miss the other stuff. Everything you've learned on one slide. Really. Ready? Here it is. That's everything you've learned on one slide. I'm not kidding. Okay, but we're going to go piece by piece through it. But this is actually everything you've learned. The part that's gray is something you haven't learned, because we're going to add to it after the exam. But everything else you've learned on the slide. This is, and not only is this everything you've learned, but this is stats in a slide. In front. That's it. That's all we do. That's all we will do for the rest of the year. And you've learned it in 4 weeks. So what do I mean by that? Well, as statisticians, as researchers, we care about something out there in the population, some phenomenon. Specifically, we care about population parameters, which is any quantitative feature of the population that we're interested in, right? So as social sciences, we design research questions that are focused on a specific effect in the population, right? We specify models that depict what we think is happening out there in the world. We depict them in pictures, we depict them in words, right? And then, so let's talk about this population piece. So population is the group we're interested in out there in the world. And a parameter is any quantifiable measure of that population. We haven't really looked at a lot of things other than the mean of a population. We've tried to estimate means. And we've been to some degree interested in variance, because that's kind of the name of the game in stats, right? We wanna know why people are different in something. If they're not different, there's no reason to do this study, right? Go home. A parameter estimate is an estimate of a population parameter that we generate using sample data. So population parameter is an actual parameter that describes the population. Parameter estimate is something that we're estimating from our sample. So what do? We sample from the population. And then we have what are called descriptive statistics. Now, an important thing that has come up a couple of times in office hours that I want to clarify, which only applies to the one sample type test that we've been doing. When we say we sample from the population, that can get confusing because we're comparing our sample to a population mean, right? When we say we sample from the population, what population are we sampling from? Is it the same one with the known parameter? No, this is what I was worried about. Insert new slide. You're given this, right? With a one sample test, you're always given this. Rather than thinking about this, yes, it's a population parameter, but for the sake of the research, the one sample research we're doing, I find it easier to just think of it as some known value or some status quo or some claim, right? The industry standard is 20 minutes. The government claims it takes 30 seconds, right? What's another one we've done? Historical average for this exam is 50, right? It never talks about a group of people. Do you notice that? Mm-hmm. When it gives you that known mu, it's never mentioning a group of people. It's always just giving you a number. And then it's saying, compare that to a sample of something, right? That sample came from a broader group of people, right? That broader group of people is the population you're sampling from. And what you're trying to figure out is you're trying to estimate from that sample the population parameters from which it came. Mm-hmm. Make sense? You don't care about this. That is fixed. You are given that. You want to know whether the population from which this sample came is different or the same from the thing we know. So clarifying, it can get confusing because we're working with the population. I'm going to leave that artwork right there. So in this case, the population parameter that we're given, the known, that's out there, right? What we have is someone tells me Verizon takes 20 minutes. That happens before this whole thing begins. And then I say, ooh, I want to know, or they say the industry standard is 20 minutes. And then I say, ooh, I wonder if Verizon takes the same amount. What's my population? Verizon customer complaints. So I reach into Verizon. I take a sample of Verizon. See the difference, right? I can't determine my population until I've already have that known thing I'm comparing to. So I reach into the population, I take my sample, right? And I describe it, right? And if I want to estimate Verizon resolution time, what is my best guess with no information other than my sample? No, I only have my sample. Anything about my sample, exactly, right? Our sample serves as an estimation of our population because it's all we've got, right? We're not saying it's great. In fact, we're going to have to determine how bad it is, right? But the point is, it's a feature, a descriptive statistic is a feature of the sample that we use to estimate the population parameter, right? Because it's all we have. It's the only access we have to that population. We don't get to take 25 samples or hundreds of that. So a sample is that subset of the group we're interested in. So we care about Verizon customer resolution time. The subset is that sample. And a descriptive statistic, sometimes I just refer to it as a statistic versus a parameter. You don't have to put the words population or sample in front of it because the word statistic and population should already signal to you sample versus population. But a statistic, just a parameter, is also a quantifiable feature of a group. It's just a different group. It's a sample instead of a population, right? Again, we have dealt mostly with means, variances, standard deviations, and effect sizes in our sample. There are other ways to describe a sample that we have looked at. The main way that we have described a sample other than those numbers are frequency distributions. And those frequency distributions can be tabular, meaning in table form, or they can be a graph. If they're in a graph, we just call them histograms. right? So same thing. So we went through the descriptive statistics before, but there are three categories of descriptive stats. The first is distribution shape or frequency distribution, measures of central tendency, and then we have variability. Quick review on these. Frequency distribution. Someone asked, please explain how to find the appropriate bins and ranges for making histograms. Never in your life are you going to go out in the world and make a histogram. So I'm not going to have you do it on an exam, right? Why do I have you do it on DA1? So you learn how a histogram works. Not going to have you build a histogram. So not going to show you how to build a histogram right now. Cool. Frequency distributions represent how frequently each outcome actually occurred. The key point with a frequency distribution is that it is a descriptive stat. Descriptive stat can only pertain to data you have in your hand, right? Meaning it has to have already occurred or been collected. So a frequency distribution is data that has already happened. When we graph it, we call it a histogram. Now, can you logically look at a histogram and make predictions, probability-based predictions? Sure, right? If I was a betting woman and I had to pick a value that was most to happen in the future, based on a frequentist perspective, I would go here or here, right? But I can't calculate a probability from a histogram because it's just representing what already happened. Cool? Measures of central tendency. A single score that meaningfully represents a set of data, a single value that has a tendency to be near the center of a distribution. We really don't deal with modes, right, in what we're doing right now, because we're dealing with continuous distributions. Mode, right, we're dealing with continuous values. Modes are much more common. We have categorical data, which we're not doing right now. So the real question becomes, when choosing a measure of central tendency, what's better, the mean or the median? You're not really, I wonder if I should pick the mode, right? If it's continuous data, I'm probably not picking the mode. So there are two questions here around how do we choose? And basically the questions are similar. They're how far apart do the mean and the median need to be? Or how skewed do the data need to be before I don't choose the mean, right? And the answer is there's no cutoff, right? It's not, there's not some magical value where it's, oh, time to use the median, right? And that's kind of how stats works, right? There's not a lot of cutoffs. You have to take into account, if I use the mean here, right? What happens to my model? How of a representation am I going to get, right? In this case, especially since we are early in the process, what I really care about is you thinking through why would I use one or the other and making a really informed call. Because as we get more into the data, you're going to have to make more informed calls about those types of things, and I want them to use sound rationale. So if you look at these two examples, I'm not going to give you one, right, where it's, I don't know, it really could go either way, right? These are two examples, right? So here you have sample one, here you have sample two. Sketching doesn't really help very much. And the reason sketching it doesn't really help is because you don't have enough numbers to make a distribution, right? If I drew you a distribution and it looks that, you could easily be a median, right? If it's really skewed, either of these, huge tail, you could be a median is better. And how do I know? Because here's how you ask yourself. You ask yourself, where does the majority of the data lie? Because that's a measure of central tendency. It should describe the typical person. So I take my highlighter and I'm, right? The majority of the data lies right here. The majority of the data lies right here, because remember the y-axis is frequency. The majority of the data lie right here. In B, the mean is a perfectly acceptable measure of central tendency, right? When everything works, we always the mean because it opens up a much broader range of statistical analyses. So when they're both fine, use the mean. Look at what happens in the two skewed distributions. The mean is not in my yellow region, right? But that's where all the data lie. And so therefore, the mean is representing a value that is not where most of the data. What is in my yellow part? Median, right? So in this case, the median, if I were to give you a distribution, right, this would be the technique I would use. I'd be like, where is the most of the data? Which of the mean or median are in that shaded area? But if I give you a sample, if I give you numbers, you can't do that because you can't build a distribution with 6 values or 7 values, right? So how do you do it? Well, you calculate both. And then you look at the numbers and you say, well, which is a better representation? So if we look at that first sample, the mean is 56 and the median is 31. And in the second sample, the mean is 29 and the median is 30. Let's start with the second sample. Easy call. What are you going to pick? Mean. You don't even need to look at the numbers. Why? Because the mean and the median are so similar that if they're that similar, you can use the mean, right? It means they're stacked, which is implying normality of some sort. What about the first one? Median. Why?
The score cluster around the median more.
The score is clustered. I mean, the way I look at it is far less statsy, right? I mean, 20, 15, 24, 32, 30, 35, 300. Whoa. 40, 20, 45. I'm already going median first. But then I'm looking at it and going, the median is 31. 31 is pretty close to most of those numbers. Right? 56 isn't close to any of those numbers, right? Median. Variance and standard deviation. Variance, measure of variability for the average squared distance that scores in a population deviate from the mean, right? There's measures of dispersion of the data. That's important, meaning it's one number that measures the dispersion of all of the data points. Right? It's very statistically helpful, right? Meaning we use it in all of our stats formulas, right? We don't actually use standard deviation very much. We use variance a lot more. Standard deviation is just the square root of that, and it helps us understand the average distance of scores, right? And the spread around the mean, and it's practically helpful. Right? It's easy to say to somebody, you are 1 standard deviation above the mean. It is not helpful to say to someone, the variance of my entire distribution is 4,327. I can't use variance to describe a single score and its position relative to the mean. I can use standard deviation to describe a single score and its position relative to the mean. Variance describes every score. Cool. Don't worry, I'm going to get into the n-1 thing. A lot of people ask about that. But let's start with sum of squares, because I promise you, there are sum of squares content on this exam. Why? Because we're about to spend 8 weeks cozying up to sum of squares in ANOVA. That's basically all ANOVA is. Sum of squares. So the first thing is sum of squared deviation unit. So we got to know what a deviation unit is in order to be able to do that. Sum of squares describes how far all the data points are from the mean. That's it. So in order to do that, we first have to just subtract how far is each data point from the mean. Those are called deviation units. But if I add up all the deviation units, so everything above the mean, everything below the mean, I get what?
0.
0. Good. So the easiest way, right, to add up all those distances and get rid of the negative is just square each of those distances and then add them up. That is your sum of squared deviations. Cool? Question, sum of squared deviations. Would you like to write down each step or compute the sum of squares in a calculator and just write down the final value? What do you think?
Right.
Hannah knows me well. Answer it. Doesn't matter. I don't care. What's the risk in not writing it down? No partial credit, right? You put down a number and it's wrong, and I don't know if you understand, right? Like I said, remember that I grade every question. I do not grade questions for right answers. I grade questions for evidence of you having the knowledge and skill that that question is meant to assess. Sometimes that means your answer looks wildly different from my key. And that's, I do not grade for the right answer. College is over. High school is over. Cool. So lots of questions about this N-1 unbiasing biasing thing. Okay, cool. So the first thing is, why do we divide by N-1? So, well, when we know the population, let's see. If we know the population mean, right, we can divide sums of squares by our actual sample size, right? So meaning if we are subtracting, think about how we calculate sums of squares. We calculate sums of squares, not with a highlighter, that's not. We calculate sums of squares by taking each point and subtracting its own sample mean. How do sample means get made? By the data points, right? So you're literally taking, it's a tautology. You're taking the point that made the mean and subtracting the mean from it, right? So you're, in some ways, you are biasing that deviation. That's a nice way of thinking about it. By calculating sum of squares this way, by subtracting its own sample mean, you're biasing your calculations because your own data points went into making the mean, right? So if we knew the real mean, if we knew mu, not x bar, right? So let's say for a second that we knew that the population mean was 100, then we could divide by n, little n, right? Because we would be seeing how far away that deviation, it would be a real deviation. It would be how far away is the data point from the actual mean, right? Then we could go ahead, we could divide by a sample of 5, and we would get 5. But do we know the population mean when we calculate a sample standard deviation? No, bless you, right? We don't. So instead, right, if we don't, check this out. Here's what happens when we don't. We have that same sample. We don't know the true population mean. We just know our sample mean. So we take each of those sums, we take that sums of squares, we divide by 5, and we get 4, right? That is always going to be an underestimate of the population mean, or sorry, of the variance, because our sample scores are artificially close to their own sample mean than they are to the population. So to account for that, right, to account for the fact that we're artificially minimizing those deviation units more than they ever really would be in real life, we divide by N-1, and we get a more realistic view of the standard deviation. Now, that's one way we've talked about variance and standard deviation is spread of data, right? The other way we've talked about variance is way bigger picture, right? It's not a descriptive stat. It's the goal of stats. And we just want to make sure we don't lose that, which is, and someone asked this question, which I was, oh, right? What happens if your sample has no variance, right? Because we always look at those descriptive stats, right? We look at variance, we look at standard deviation, which are basically the same thing. What happens if your sample has no variance? Take a second. I don't want to hear it. I want everyone to think about this for a second. Let me give you a context that might help. You're studying the effect of your intervention on well-being. You get back your data and you find that your well-being scores have a variance of, I don't know, 0.01, 0.03. What do? What does that mean, first of all? Start there.
Everyone scored the same.
Right? That think what drawing a distribution with a variance of 0.03 would look, it's right? There's no distribution because there's no spread, right? This. So if you're trying to predict that outcome, there's no high, low in the middle to predict. Go home, do it again, right? You screwed up somewhere. That's the other really important piece. And that's why, this is one of the big reasons why. So we check descriptive stats always. But one of the reasons why we check variance in particular is, one, it shows us the shape of the distribution, the spread. It shows us things outliers, but it also shows us how much spread do we have in the thing we're trying to model, right? If we have no variance and no standard deviation in the thing we're trying to model, your study, your model is dead in the water. You have to go back to the drawing board. You're done. Colleen.
It necessarily true that there is an error if there's no variance.
If there's no variance, it is most that you made some sort of mistake along the way. Think about what you're studying, right? Let's take well-being. We know that not everybody in the world has the same well-being, right? So it could be the measure you use, and it's something you did before you collected the data, right? Because all you've done at this point, think about the drawing, right? Think about this drawing. Nope, we're not even there yet. Think about this drawing. All you have done at this point is sample, literally, right? You haven't done any stats. You're just describing your sample. So it has to be something you did in that sampling ring, right? Could be the measure Heather just said, could be where you sampled. If you did an experiment, could be something you screwed up in the experiment, right? Not unless you had 2 or 3, right? Like a really crazy small sample.
Somehow you sampled, but
Or some, I guess it depends on what the construct is. Maybe you sampled, that could be, maybe you sampled, but that wouldn't be size. It would be location. So maybe you sampled everybody in, I don't know, Mrs. R's class, which is Camila's teacher, right? And they all had the same level of reading because Mrs. R is a really reading teacher, right? Well, they have no variance, but that's not a sample size issue as much as it is you only sampled from one.
essentially it's indicating something's going on with your method.
Yes, it's a methodological problem. Exactly.
I get that and I understand that theoretically, and I know this wouldn't happen, but let's say you went into the future and you grabbed a pill that cured MS and you came back and everybody you gave it to was cured. You'd have no variance if everything was done right. I mean, it's not.
But you would not be running this type of test in that case. You would be running a pre-post test and you would have their pre-scores and it wouldn't matter. To be talked about post-exam. But yes, in that case, it would be because people would still change to different degrees from their pre-scores. You'd have beautiful. Heather just said everyone might be cured, but you would have variance in the change. And that's actually what we look at when we look at pre-post. We don't look at post, we look at the distribution of change post-exam. So we've got the population of interest from which our sample comes. We pull the sample, we describe the crap out of that sample, right? And we're right? The mean of Verizon complaints is 22 minutes and 30 seconds. So is that industry standard? I don't know. It seems it's more, right? Because the industry standard is 20 and 22 is more than 20, right? But I don't know how much more that is. So I have to evaluate that sample statistic, right? And the meaning of that stat depends on the accuracy of my sample, right? I can only evaluate that thing I found about my sample, the descriptive statistic, in the context of how off my sample is going to be from my population. Enter standard. Take a break. It's 10:06. Come back at 10:15, but a lot left. Lot left. Not a lot of time. I always, it's year 5 of teaching this class, still somehow think I can do reviews in 2 hours. I think next year, put this on the improvement doc. Next year, I just need to be reviews at 3. There's no way. I just can't do it.
Yes, every year.
Especially in A. But I figure out a plan. So we've got our descriptive stats. We've described our sample, but we know that that sample is not a perfect description of the population, right? So before we use that sample data to figure out the population for parameters from which that sample came, remember that? Not the known value, the population from which that sample came. Before we do that, we have to determine how our sample is, how good representation it is. More importantly, or more specifically, what we're going to determine is not how it is, but how off it's to be, right? How bad it's to be. That's standard error. Now, standard error is ultimately what we care about when it comes to all things probability and null hypothesis testing. But you have to understand probability. There's a precursor to standard error and hypothesis testing, which is probability 101 and finding probabilities under distributions. There's no place to put it in this graph because it is not a step in the process, but it is all over here, right? Without understanding how to calculate probability of things, you can't do anything in this red part of the process. So we're going to take a little detour away into the probability type of stuff that we've done. Oh, I did start with sampling distributions. I lied. Sorry. So we've got our descriptive stats. We're going to evaluate that sample statistic, right? Based on how off that particular sample is going to be. We're good? We're good? We're good? There's stats, yes? No, you're fine. Cool. So sampling distributions. Sampling distributions are theoretical probability distributions of a statistic. Remember, we just described our sample. So we just got a bunch of statistics of our sample. So the sampling distribution tells us the probability of getting that statistic we just got, right, from a particular population, right? So it tells us the probability of pulling a particular sample statistic, right? It's built theoretically, meaning we don't build it, right? It's theoretical. It's essentially happens, or it's theoretically constructed as if you were to pull every possible sample under the sun and calculate the sample statistic. In this case, we've only been dealing with means, right? So you are essentially taking infinite numbers of samples, and for each sample, you're calculating a mean. Once you do that, if you had that, if someone magically gave that to you, right, then you could use that distribution to find the probability of your specific sample mean, right? You could be, well, my sample's mean was 22.43. How off is that from truth, right? Cool, that would be awesome. We don't have that actual real theoretical distribution, right? But we can estimate it in our studies. Now, what's the actual quantitative measure that we care about in this theoretical distribution? It's standard error, right? Standard error, right? If this whole picture represents how off, let's say this is our sample. How do we figure out, just visually, let's go back to this one. If we want to know how off our sample is from the real population parameter, how could we describe that? How could you describe that in two ways?
How far it is in terms of standard deviation.
So there's two options, right? One, you could take your sample and subtract it, right? Think about this. If I want to know how far away I am from Heather, there are two ways I can do it. I can subtract and measure. I am 3 feet away from Heather. Or I can say I am 0.3 standard deviations away from Heather. Those are your two options, right? Same here. I can say this sample mean is, I don't know, let's say 10. If I had all the actual numbers, if I had this real distribution, I could say the sample mean is 20 points off from the real population mean. I don't have it, so I can't do that, right? Or I could say the sample mean is, 1.5 standard deviations away from the mean, right? So the standard deviation of this imaginative theoretical distribution represents how far away all these potential, bless you, sample means are from the population. So because that standard deviation is a measure of spread, the standard deviation of this distribution tells us how far away any one sample mean is to be from the real population mean, right? That is why standard deviation of the sampling distribution is called standard error, right? It is giving us the spread of all possible sample means. In this case, spread of sample means is not, right? We don't want our sample to be far away from the population. We want our sample to be very representative and very close to accurate. So the more standard deviations away our sample is from the population, the more off our sample is. So what is it conceptually? If we had to describe what is standard error, Well, you could describe it in a lot of different ways. You could say, if someone asked me, hey, what's standard error? I could be like, oh, it's the standard deviation of the sampling distribution. That's one correct definition. That's the literal mathematical definition. But if you were, what is standard error? I would be like, it's how off a sample is from the true population, right? How off a sample statistic is going to be. So you should be able to describe that standard error in both ways, right? In multiple ways.
Our sampling distribution is also theoretical and infinite.
Say it again.
So since it's of the sampling distribution is also, we have a number, but it's also infinite. The sampling,
If we have a number, how could it be theoretical and infinite?
so it's measuring something that it is, or the number that it's talking about.
Well, any normal distribution that's asymptotic can still have a standard deviation, right? We just know that if it's perfectly normally distributed, which sampling distributions are, that by the time you get out in the tails, even though they're asymptotic, they don't touch. It's like 0, 0, 0, 0, 0. Standard error of the mean, which is the one we've worked with, measures how much discrepancy there's to be between our sample mean, right? And the true population mean, not the status quo thing we're comparing to. This is really important distinction. The true population mean from which our sample was drawn, meaning the population mean we're trying to represent from our sample. Remember that our sample is standing in for our population. That's what we're trying to do here, right? So it's saying how off or how representative is our sample to be of the population from which we pulled it. Standard error is saying this is how off that sample is from the population from which you pulled it. If we know the population standard deviation, then we can actually calculate the standard error, right? If we don't, then we can calculate the estimated standard error. The formula is the same. It is the spread that we have access to over the square root of sample size. Now, why, if the sampling distribution is theoretical, how do we do this, right? Well, it's because these two things are the two things that influence how off a sample is to be, right? Think about it. The sample size one is super easy, right? If I take a tiny sample, I will be more off from the population, right? That one's conceptually easier to wrap our head around. If I take a big sample, I got more people. I got more of the population. The top one is a little harder, right? Why does spread of the population or spread of the sample make me more or less accurate as a sample? Well, let's look at this one. Assuming this is the Y, what impacts standard error? Again, sample size, easy. Why the spread part? So let's assume for a second that you're trying to estimate quality of food at a restaurant. So here's your first sample. N equals 5. And the ratings are 1, 10, 1, 10, 5. Here's sample 2. 10, 10, 9, 10, 10. Here's sample 3. 10, 10, 10, 9, 9, 10, 10, 10, 10, 10. Which one do you think is giving you the best, most accurate insight into the quality of the restaurant? Why? So 1, it's got more people. Cool. Let's take that out of the mix. Now tell me which one. They've got the same number of people. Now which one do you think is giving you a better estimate of the food?
2,
Why?
less spread.
But why? So fine. Why? Why does less spread make you have to decide, are you going to the new restaurant or not? Why would you go if sample 2 told you versus sample 1? It's more consistent, right? More consistent in statistical language means less spread, right? So if your sample or your population is not all over the place, then you have less to pull from in your sample. Here's another way of looking at it. If your population or your sample looks this, and the lowest value is 10, and the highest value is 30. See that? When I reach into that population and I pull values for a sample mean, even if every value I pull is 10, what's the lowest mean I could possibly have? 10, right? What's the highest mean I could possibly have? 30. If my population goes from 10 to 1,000, right? Well, what's the lowest mean I could have? 10. What's the highest mean I could have? 1,000. But what's the actual mean of this? They could be exactly the same, right? So the issue is when your data are spread and you're pulling one single sample, you are far more likely to pull a mean that is not close to the true population mean. Right? That we understand now why that spread matters. Sweet. Sample size is easy. You got more. Oops. And this same principle that I showed you with samples, right? This works with populations. It's the same exact concept, right? If your population is more spread or your sample is more spread, it's the same idea. If your sample is more spread, it's because your population was more spread, and therefore you grabbed more extreme values to create that sample. Couple central limit theorem pieces. Is the central limit theorem, oh, there was one question we missed here. It's small, so I skipped it. I don't know why we divide n-1 when calculating the standard error of the mean. I know we don't divide by n-1 when calculating standard error of the mean, but I don't think I can describe why. Can we revisit that? Yes. The reason we don't divide by n-1 is because we already did. Right? So if we know the population, right, we don't need to divide by n-1 because we know the actual population variance and standard deviation. If we don't, if we're estimating, we do need to account for that, but we already did when we calculated the sample standard deviation. So remember that sample variance is sums of squares over n-1. Right? That's this. And so we've already accounted for n-1. We don't have to do it again. Oh, I really want to answer this question. This. In the central limit theorem, the reason or the why behind why the sample mean is an unbiased estimator of the population mean. Wouldn't the sample mean technically be a biased estimator if it fails to equal the population mean? Your one sample mean is not your population mean, right? The mean of means is equal to the population mean, not your one sample mean. Right? Your one sample mean is going to be off from the population mean. That's why when we hypothesis test, right, we're actually going, here's what I got, but also here's my error, as in how off is that mean to be, right? It's not an unbiased estimator. The mean of means, meaning if I were to take not one sample, but infinite samples and average them, that would equal the true population mean. I've said this to a couple of people, but the way I think about principle number one is this. If you're Galileo and you're trying to find the exact position of a star and you're using a telescope and not a 2024 telescope, right? You're looking at that star has an exact location, yes? You take that telescope and you fixate as well as you can on that star and you write down its measurement. You're not exact, because you're a human and your hands are shaking and you're a little bit off, right? You write down your first measurement and you take another measurement. This time you're a little bit off again, but you're a little above it this time. You write down your measurement, right? Then you do it again, you're a little bit to the right, you write down your measurement. If you were to do that infinite number of times and be a tiny bit off in random directions every time, and then you average all of those measurements, guess what you would have? The exact coordinate of the star. Right? That's the concept of the sampling distribution of means. If you were to take infinite number of samples, each individual sample would be off to some degree, some high, some low. If you average them all, you would get the exact population mean from which those samples came. Yes, it has 3 parts right there. This part is only one part. Yes, that sampling distribution will be normally distributed because the average of all those means is straight in the middle. And half of your means will be too high and half of your infinite means will be too low, regardless of what that original distribution looks like. Here's the plan with z-scores. Here's what I did. You know there are going to be z-score problems on the exam, right? Both single score z-score problems and sampling distribution z-score problems. I put all of your sample problems on a separate slide, this. What I'm going to do for time's sake is skip them for now, because worst case scenario, Rater can run through all of them at 11 if you want to stay, right? What I don't want to do is leave you without me reviewing how our hypothesis testing effect size. That would be bad. So we're going to skip those, but they're all laid out for you. And these are the ones, the things that people picked were these are also really ones to run through in office hours in the next day. So we took our population, we pulled a sample, we described that sample, but we said, hold on, we have to consider that sample in the context of how off it's to be from our population, right? Well, if we have our effect, meaning what we found, and we have this measure of error, right? We can use those two values to actually create what we call a test statistic. And that test statistic is what we can use to test our original hypotheses. So what is a test statistic? It is a value that expresses our sample statistic relative to the accuracy of our sample. That's it. So it is a statistic you calculate for use in hypothesis testing. We've only used Z and T. It's always the proportion of two things. It's the difference between your sample mean and whatever the known population thing is, and error. In fact, that ratio of effect and error is essentially almost every test statistic under the sun, even the ones we haven't learned yet, right? The concept of stats is collect data, consider it as an estimate of what's going on in the world, but only in proportion to how wrong it might be. That is stats. That's inferential stats right there, right? So oftentimes we're looking at a proportion of effect to error. And what you can see is in the two that we've learned, the top is our effect. How far away is the sample we got from the thing we know? Verizon took 22.3 minutes. The average industry time is 20. How far away is that? Not rocket science, 2.3 minutes. Don't overthink it, right? But 2.3 minutes, is that a lot? Is that a little? I don't know. We gotta figure that out. We gotta be able to test that number, right? And that number is only as meaningful as our sample or bad our sample is. So we always have that in proportion to how off our one single sample is to be from the true population. So it's always effect over standard error. Now, for us, it's standard error, but this thing, this whole conceptual concept, that's going to hold true for a real long time. Effect over. We only know two test statistics, Z and T. Don't let those be confused with sample statistics, which are just descriptive numbers about a sample. So we have Z and we have T. We know that when we know the population variance / standard deviation, we can run a Z-test, right? When we don't, automatically we have to run a T-test. But why? Well, when we don't know the population standard deviation or variance, we have to estimate it, right? But the problem is that our sample is only as, right, as the number of people that we capture. So we have to use a distribution that considers how many people we were able to capture in our sample, right? In a Z distribution, how many Z distributions are there? What? So in a Z distribution, the probability of a given sample never changes based on sample size, right? It's one curve, whether your sample has 30 people, 50 people, 70 people, or 10,000 people, right? If you know the population variance and you're using a Z distribution, it doesn't matter how many people you have in terms of your critical value. Sure, it goes into your standard error, but in terms of where the cutoff value is, that 1.96, that doesn't change. In a T distribution, the probability of a given sample result does change based on sample size, i.e. degrees of freedom. More specifically, the critical value where your cutoff is going to be to achieve statistical significance will change based on degrees of freedom. Here's what I mean. Here's a standard normal distribution. We know we have an alpha of 0.05, right? Meaning if we are more extreme than 0.05 and the Z or T that belong to that, we're going to reject the null hypothesis, right? For Z, two tail, that's 1.96, always, no matter what, right? For T, it depends on the sample size, right? For degrees of freedom 5, because it's so wide, to get 5% or 0.05% in both tails, you have to be way out here, right? But for degrees of freedom 30, you can be here. And this is the same axis. So this might be a T of 1.4, and this is a T of 3.2. I'm just making up those numbers, right? So basically, before we reject the null hypothesis, if our sample is small, we have to have a far more extreme value when our degrees of freedom is small, when our sample size is small, okay? Because we are estimating, right? We are estimating that standard error. We don't know it.
Hey, Jess, can I ask a question? When it says on the chart here, degrees of freedom equals 30, and it's identical to the standard normal distribution, if we were ever to be working through a problem where our degrees of freedom on a t-test was ended up being 30, would that be the same thing as the normal distribution as if we calculated it with the population standard deviation?
So question. So once you get up to anything degrees of freedom 30, it approximates a normal distribution, right? It's always a normal distribution. It approximates the standard normal distribution as in Z, right? So Z is T with a really big sample size, basically.
It's frozen for me too, Jess.
Cool. I was getting worried there for a second. Let's see.
This is a great time for that to happen.
She was probably already done, and we're just sitting here.
Because she said the word power. She probably said the word power, and I think it just.
Oh, Quinn, they will be right back. They know we're out.
They probably cares.
We're languishing out here in self-doubt. Does anyone know, if the standard deviation is known, but the sample is under 30, we use a t-test because that more accounts for the n? Is that what I'm?
You need a more extreme value.
Great, helpful. And that's why the n under 30, it comes from this idea that the degrees of freedom once you reach 30 is the same as the z, basically. So that's where that aligns.
That kind of confused me because it contradicts what she said the other day and what's in the book. Because if you look at 30 degrees of freedom and then you look back at the z table, it's not the same number. Only when you get to infinity is it the same number. So
is it getting
starts getting closer?
Okay,
Probably still recording FYI, so don't say any curse words.
Exactly.
Don't say any wrong answers.
But I'm wondering if they're just simplifying it for us, because you guys have noticed how after that first degree of freedom, it went from 12 and then it went to the 1. So I just feel maybe it just becomes so infinitesimally small past 30 that practicality wise, they're just going to kind of consider it that it's so for most 99% of people, you're not going to really need degrees of freedom past 30 because it would just kind of equate to the same thing. I mean, how different is the number, Alan? Because I don't know.
I mean, got my
it may not be an exact thing, because I thought she said once it gets to 30, it starts to approximate the standard
right
distribution.
For degrees of freedom 30 two-tailed alpha, it's 2.042. When you go to 40, it's 2.021, 60 is 2, 120 is 1.98, and then at infinity you get to 1.96, which is the equivalency. So you can see incrementing down. I think it's the amount that it increments down reduces pretty dramatically.
I almost wanted it to clarify that again, because if there's a question that has 30 degrees of freedom on it, it's going to be a different critical value on the t-test than it will be on the z-test.
But remember, she said if you find it on the t-test, you'll find it on the z-test.
Right.
So the sort of default is t, right?
Oh, are we back?
When in doubt, t-test.
Should we stop? Can everyone see the screen? Quinn, can you also hear us? What's going on here? Are we just podcasting to the?
I think we are.
Oh, we're back.
Down thing. Oh, what happened?
You change it back to seven.
AJ, can you hear me?
Yeah, I can hear you really clearly. So it might just be because of the classroom. So I hear you clearly.
So Z and T, so Z and T, you can always use T because as their sample size gets big enough, it just is the same as Z, right? Also, don't get mired in the weeds here. Back up. Why do we need Z and T distributions, y'all? What's the point from a research perspective?
Scores.
Because we
What?
don't always have all the
Standardized
information.
scores.
Sorry, I overtalked. Isaiah, go ahead.
To standardize the scores.
So that's why we use Z distributions, but big picture in research, what is the utility of T's and Z's?
Differences.
They're test statistics, right? They help us test our hypotheses in research, right? So really what we're doing is we're using them to make inferences along with a lot of other information, right? Effect sizes and directionality and confidence intervals, which we'll learn later, right? And so my N is 29, my N is 30, my N is 31. Which should that isn't going to change our decisions at the end of the day, right? So we have a tendency sometimes to get really mired in the weeds, and that's because majority of you went through US American schooling where they teach you to get in the weeds. Yeah. Don't forget, stats is a tool, right? You can get too sucked in the detail. And as a result, you have to trust me that I don't give you examples that are gonna make you hem and haw over detail, right? I will not give you N equals 30 and make you go, oh, I don't know, should I use T or Z? That is not a use of your intellectual capacity. I will never do that, right? I will to direct your cognitive energy in the right way, which is not that. Trust me. Where were we? Oh, here's an actual real, these are the real cutoffs. So these are the actual for alpha equals 0.05. This is what the cutoffs look at different degrees of freedom. So this is what you would have to get as your T calc in order to reject the null hypothesis at each sample size. So see how extreme, if you had a really small sample, degrees of freedom 3, it's crazy, right? You would have to be way out there in order to reject the null hypothesis. Now, to Travis's question, here's your slide. Karen, that's for you. Okay. So yes, you should always think about degrees of freedom as the number of pieces of information that you have minus the number of parameters being estimated. That equals degrees of freedom. I insist on teaching it to you in the right way so you don't have to unlearn it later. But you're right that right now, the only two things we end up with for the only two tests you know are both N-1. You're not wrong. I just care that you know why, right? So if you think about this, right? This is what or how. Cool, you're right. I care that you understand why, right? So the idea is, guess what drives our research question? It's not the test or our degrees of freedom. It's the research question, right? So our research question is, does our sample differ significantly from a known population parameter? So here we have a known parameter, and here we have this sample. So what do we have to estimate? We have to estimate the population mean that this sample came from. That is the only population parameter that we are estimating. So we are estimating one thing. We have however many data points we have, which in this case is just our sample size. So in this case, it's N-1. But it's helpful to know the why, because you've got to be able to wrap your head around the idea that, of course, I'm estimating one thing in this test. But the how, N-1. So now we've got our test statistic. Cool. Well, now we're going to put that stuff together into null hypothesis significance testing. And we're going to ask ourselves this really important question, which is, how is it to find that test statistic I just calculated if there's really nothing going on? That's null hypothesis significance testing in a nutshell. This is the last thing I'll lecture on, and then we'll. The NHST questions don't really belong on one slide, so I just dumped them on the title slide. But so what is why is the type 1 error considered alpha? Love it. Do we need to know a priori power calculation? No, but you definitely need to know that it is an a priori thing, and we'll get to that. What does it mean when we say NHST is biased by sample size? We'll get there. How would we interpret power as a value? Would you be able to give an example of why power is important? Sure. Can you go over power conceptually and in relation to type 1 error? Sure. Do we change how we calculate beta and 1 minus beta for a 1-tailed test versus a 2-tailed test? The first thing I want to do is just look at this curve and make one thing super clear. These two curves, let's call them worlds. These two worlds are separate from each other, right? They don't exist on the same plane. I have them overlapping, right? Because that's kind of how we think about it when we're hypothesis testing, right? But the only known reality to us is what?
No.
The null. We know the null mean, right? We know that. We don't know anything about this alternative world. It could be here. It could be here. It could be here. Heck, it could be here, right? So we can't ever calculate actual beta or actual power, right? Really, in truth. Like if there's no way to be, I know I made a type 2 error. You can't do that, right? You're never gonna know. Mistake. So there isn't a time where we calculate beta or power after the fact. Okay, I'll get to the power part in a second. I want to go through the 4 possible outcomes way more in depth than we have before in an effort to talk through the different regions and also the different types of error. So we're going to go through each of the 4 possible outcomes, right? True negative, true positive at E power, type 1 error, type 2 error, right? Type 1 error is equal to alpha, type 2 error is equal to beta. Notice we know this one, don't we? We don't know this one. Do we know this one? Do we know this one or not? We said it, right? What's the probability of making a type 1 error? 0.05. You just said it, right? If you decided to set your alpha rate at 0.01, then the probability of making a type 1 error would be 0.01, right? That's the one we do know. Why? Because it's under the null curve. We make decisions, we know things under the null curve. We know nothing under the alternative curve because we're just making estimates about that world. That's a population that is unknown to us that we are just estimating. We're going to go through each of these. First things first, remember that NHST is all about testing our result against nothingness, as in testing it against the null. That informs the language we use when we make a conclusion. That informs how we make decisions about whether something's happening. Everything is against the null. So if we obtain a calculated value that is over here, right? T-calc, let's say, of 1.85. What do we make of this? Well, if we're going to interpret this value, literally what this means, think about the ratio of a T. What's the ratio? It's what and what? Effect and error, right? So if a T is 1.85, that means there's 1.85 times more effect than error, right? Cool. You can also say that this result is 1.85 standard error units away from the mean. That's another way of interpreting it. Can't say standard deviation units. You can for a z-score, can't for a t-score, because there's multiple t distributions, right? Not one. Now, how do we interpret the result? Well, what we're saying is, based on our sample, we're deciding not to reject the null and conclude that there's something going on, right? Meaning we don't have sufficient evidence. I used this analogy yesterday. Can I use it? So we use this analogy that actually ended up working all the way through. I'm obsessed with all things sushi and sashimi. I could eat it every day for the rest of my life. And so we were, let's say that this is your current favorite restaurant. And you're like, this is my favorite restaurant. I love the food, I love the ambiance, I love the staff, right? And someone's, you know what? go try this other one and see if it's significantly better than your status quo restaurant, right? So you go and you try it, it's better, right? But man, it's not that much better, right? And really the waitress that always serves you on Fridays, right? And so you're like, you know what? It's not better enough that I'm giving up my status quo. That is the concept of rejecting or not rejecting the no, right? Is my difference extreme enough that I'm willing to let go of my beloved status quo sushi restaurant? Make sense? See, it works. It kind of works. Now the question is, what's really happening? So we already made a decision. That's the important part, right? The decision is what guides the everything else. Decision comes first. We don't know what's happening under the hood. We make a decision. So in this case, we have said, no, we are failing to reject the null hypothesis, or we could say we are retaining the null hypothesis, right? We are retaining our beloved sushi restaurant, or we are failing to reject our beloved sushi restaurant. But what's really happening, right, under the hood? I'm not going to worry about the p-value because I think I drilled that enough. Well, there are two options for what is happening under the hood. Assuming I've already said no, I'm keeping my null. Here's option one. Option one is that actually this new sushi joint, it is not any better than my null sushi joint, my status quo. I had a particularly dish that day, so it was a little bit better, but on average, it's no different. On average, its average is exactly the same as my current sushi restaurant's average. There's no difference. I had a sample of what they offered, and its T was 1.85. But if I were to take everything on the menu, as in the population from which that sample came, it would be no different than my current restaurant. It would be in that is true negative. Make sense? That's option one, right? That is 1 minus alpha. Notice, what are these black things? I know that sounds a weird question. Just go with it. What are those? It's not a trick question. No, what is this? What is this?
Distribution?
It's a distribution curve, which means it is equal underneath to what? People forget. I say that, but you all forget that these are probabilities, right? People forget that this isn't just a rejection region, it's a probability of making a type 1 error, right? People forget that the actual probability of getting a true negative is 1 minus 0.05. So if I asked you, what's the probability of getting a true negative? A lot of you would go, I don't know. Because you forget that that's a distribution that's equal to 1, right? The answer is 0.95. You know it. It's a number, right? Same with what's the probability of getting a type 1 error? You know it. It's 0.05, right? It's a number. So option 1 is, right, true negative. Outcome 1, true negative. What we're saying here is there's a 0.95 probability of correctly retaining the null hypothesis. That is, you retain it and there really is no effect, right? Another way to say it is you keep your beloved sushi restaurant, right? And that's because the other one really isn't any better. And this example works because we're comparing to a known entity, which is what we do in a one sample test. We know everything about our current sushi restaurant. We know everything about that population. It's a known entity. What's outcome 2? Well, outcome 2 is that we make a type 2 error. So again, remember, this is the same conclusion. We've already kept our old sushi restaurant. We've already retained the null, right? But there's a possibility, I'll use the analogy first and then I'll show you on the graph. What happens if actually I just happen to try one of the crappier dishes at the new restaurant? And in fact, if I ate everything on the menu, i.e. I had full access to the population from which that one dish came, I'd be like, shit, this place is right? But I didn't. I only tasted a sampling of what they, right? And it wasn't enough to give up my beloved sushi joint, right? In that case, right, it's just not the best thing my alternative hypothesis offers, right? But it wasn't extreme enough. It wasn't enough for me to give up my null. Now, from a hypothesis testing perspective, it wasn't in my rejection region, meaning there was something more, the probability of getting this, assuming this was true, was something more than 0.05. So I was not comfortable rejecting the null. So if we calculated a t anywhere in this range, you see that? We would do what? We'd retain, right? Anything to the left of that red bar, we would retain. If for some reason it's actually better, right? Then we would fail to detect that effect, and that would be a type 2 error. We can't calculate that probability because it's in the world we don't know, right? Think about the restaurant. I went in, I tried one dish, right? That's all I know about the restaurant, right? So I have no way of knowing where on that curve that one dish was, right? So that's type 2. Both of those are potential realities under my decision of retaining the null. So this is the probability of incorrectly retaining the null hypothesis. That is, you retain it, but there is actually an effect. In the case of what we've been doing, there is actually a difference between your sample mean and our known population, right? Bless you. We don't know what it is, right? We don't know what that known population is. We can say the probability is equal to beta, but we can't give you a number, right? Whereas for alpha, I can give you a number. Again, remember that NHST is about testing everything against the null. So now let's go to conclusion number 2, which is, what are we going to do? Reject. So I go to the new sushi restaurant. I sample a small number of dishes, right? Dang, those are amazing. Bye-bye, old sushi restaurant, right? Reject the null. Now, I don't accept, here's a really reason, a really example why we don't say, I accept the alternative as best. Why not? I have the sushi example for this reason, which is, am I concluding that this new place is the best sushi restaurant in the world? No, there is a better one out there, right? But for now, I've rejected the old one and I'm going with this for now, right? So I haven't made a decision to accept this as my be-all end-all sushi restaurant for here in all eternity. I have just made a decision to reject this. Okay, that's why we never say the alternative is true. The alternative is accepted. We just say reject the null. Right? That's literally, if we reject the null, that is your only option. If we retain the null, you can say fail to reject the null. But if you want to keep it real simple in your mind, I think I made someone write on their cheat sheet, retain or reject. That is the only option. That's it. They're only options. So in this case, we are rejecting the null hypothesis. Something is going on. Now, how do we interpret this? There's 4, let's say it's the t-calc is 4.85. There's 4.85 times more effect than error, right? Your result is 4.85 standard error units away. But now let's look at, right? I'm not going to do p-value again. Look at this. Now let's look at the outcomes. Here's a negative version, by the way. I did a negative one. So, oh no, I didn't. I did a positive one. So outcome number 1. So first of all, no matter what, because it's in this rejection region, right? Based on our sample results, we decided to reject the null and conclude that there is an effect. But again, we don't know what's happening in the population. There are 2 potential outcomes, right? The first is that there isn't anything going on in the restaurant. Or sorry, in the restaurant, in the population. In that case, we would be incorrectly rejecting the null, right? In the sushi example, I went in, I sampled a few dishes, and I happened to get the best thing they had. And from those best dishes, I concluded that this new place was better, right? But if I'd tried everything, I would have been on whole, it's not any better than my old place, right? I just got an extreme value. So we incorrectly rejected the null, right? We know of this happening. We know the probability of this happening. It's 0.05, right? We know it. It's under the null. Now, the other option, right? The other option is if there really is an effect in the population, meaning if this restaurant really is better, the new one, right? And it's anywhere in this region, right? Then we would be correctly rejecting the null. usually as researchers, this is what we want to do, right? We want there to be an effect and we want to find it. If I shade that whole region in, right, that's power. Notice power includes the alpha region. Why? Because alpha is under the null curve and power is under the alternative curve. They overlap, right? Because this green line overlaps. I'm going to reject, if I get anything in here, right, I'm going to reject the null. If I'm wrong, I'm red. If I'm right, I'm green. See that? That's why they're both in that region. Same conclusion, reject the null. But if I'm wrong, I've made a type 1 error. If I'm right, I found an effect that's really there. Woohoo. Power, here's an important thing. Power is a probability. Don't forget that, right? So a power of 0.8 means there's a 0.8 probability of there being an effect in the population, and we find it. Finding it means we conclude statistical significance, right, in our sample. Now, what comes next? I don't want to do that one yet. I want to do this. Now, let's talk about statistical significance and power. Statistical significance is the conclusion that we make. Power is a probability. That's how they're different. How are they the same though?
She froze.
Did
at the
she freeze
back.
again?
Finding muted. Well, fun. Having fun. Good. Finding an effect that's really there, right? So I want to go actually to the next slide. Do I have
Jess,
this
can
one?
you go back where you paused at the critical juncture?
Yep.
You were how they were
Yeah, I said.
the same.
I want to move this too. I was saying statistical significance is a conclusion we make as a researcher. Power is a probability, right? So when we decide to reject or retain is to determine statistical significance. It's a binary conclusion that we make, right? Power is the probability of finding an effect. So finding an effect is concluding statistical significance, right? But the key is it's finding an effect that's true, that's really there. If I conclude statistical significance, does that imply there's actually an effect? What's the other option? Type 1 error, right? All statistical significance means is I rejected the null, right? If I think about this chart right here, right? This is the easy way to think about it. Look, if I reject the null, that is statistical significance, right? I'm saying, world, nuts make you statistically significantly more healthy, right? I can either be right or I can be wrong. But power is the probability of rejecting the null that is actually false, right? So finding an effect that's really there. Here's another way of looking at it. We start with the conclusion, but then once we make that conclusion, we could be right, in which case power, or we could be wrong and make a type 1, right? So they're similar in the sense that they both involve a conclusion of statistical significance, but they're different in that concluding statistical significance does not necessarily mean that you found that there is an effect in the population. So let's look at these 4 things: effect size, sample size, statistical significance, and power, and clarify a couple of things about when they get established. So we know that effect size is the magnitude of effect, right? In this case, it's going to be the difference between our known population number and our sample and our population from which we drew the sample. This happens pre-analysis, right? What do I mean by that? The effect is what the effect is, right? Advo works or it doesn't, right? Now, you can still, I put an asterisk here. Why? For a couple of reasons. 2 reasons, you can write this down. Why did Jess write an asterisk? 2 reasons. 1, because you can impact dosage, right? You can impact effect size by increasing dosage. That will increase power. The other reason I wrote an asterisk is because we do also calculate an actual effect size for the study we're running, right? And that's based on the actual dimensions of that study. What effect did we get in this study? What sample size did we use in this study, right? That's not the effect of this phenomenon. That's the effect size in this study. So those are the two asterisks. The actual effect, things work or they don't, right? So it's misleading to be, I can manipulate effect size, but you can increase dosage and you can calculate an effect size for a particular study, which we did with Cohen's d. Sample size. This one's easy. Number of people in your sample. When do we decide that? Pre-analysis, right? Pre-analysis. Never. We never decide it. Pre-analysis. Who decides it? You decide, right? Statistical significance. When do we decide it? After analysis, who decides? Right? Post-analysis, right? Do you entirely decide? No. You make the call, but it's a function of your effect size, right? Your sample size, your error, and your alpha rate, right? Where's that cutoff going to lie? But you call it post-analysis. And then the last one is power. Here's a tricky one, right? When does power get set? Hold on. When does power get set? Think. Go ahead. Chloe, go ahead. Why? Can you think about why though? You're fine. Think about the definition. What is it? It's a what? So probability automatically implies something in the future, right? So the idea is we're designing a study and we want to find an effect, assuming there is one, right? So we want the probability of finding it before we run it to be high. That's why it's before, right? This is the thing people mix up all the time. Power is pre-analysis, right? What we do is we say, let's assume there's an effect out there, right? And in fact, not only do we assume there's an effect, we actually get to predict how big we think that effect will be. And then we say, I want to set power at 0.8. What does that mean? It means assuming there's an effect, I want there to be an 0.8 probability that I will find that effect, right? I can set power at 0.9. I want their probability of finding an effect, assuming it's there, to be 0.9. You can actually do that power calculation. It's called an a priori, meaning before, power analysis. The way you do that is you say, this is the effect I think I'm going to find. This is the Cohen's d, literally, I think I'm going to get. 0.1, 0.2, 0.3, right? If I want a power of 0.9, how many people do I need, right? Now, there's trade-offs, right? You want high power, right? You got to trade off other things. Why wouldn't you just always do 100%? Well, one, you can never be 100%, but even if you were 99, you're not going to collect data from 100,000 people, usually, right? So there's trade-offs. But power is a priori, and that is a big mistake. People think it's just a concept. It's a probability of once you run your research study, it is set, right? Based on the way you designed your study and the data you collected, it's done. The probability of you finding that effect is there already. You cannot change it. So now, how do we drive that power before we get started, right? Because that's one of the number one things we want to think about as researchers when designing studies, right? Is how do we increase the power of our study, right? You'll hear this term all the time. Oh, she was underpowered. Oh, they were underpowered. Oh, that study was underpowered.
Before we go too far, so you could say that you decide the power, is that correct? Or is the power?
No. The power is pre-decided, but you can influence it. Right? Sample size, where truly the sample size cannot get created unless you decide, right? Whereas with the power will be what it is if you don't influence it. Make sense? But it's influenceable. In fact, mostly through these ways. So let's talk about effect size, sample size, and power. So I added a bar to this one per Rader's comment at the beginning here. So we had this graph on Tuesday, but I added this first bar, which is instead of just medium effect and large effect, I added negligible or no real effect, right? And I changed that bar from power to statistical significance because really we don't know whether our conclusion is right or not, right? We just make a call if something is statistically significant or not, and then we roll with that. So ultimately, we're running around telling people they should eat nuts, right? And but we're doing it without an effect size. And so the reality is there are lots of ways to achieve statistical significance. And it has to do with the combination of effect size and sample size. If your effect is large, right, then you don't need a lot of people. If your effect is small or medium, you need 4 people. If your effect is negligible, or what I would call no practical meaning or no practical significance, then you need a lot of people. But I that Siegel quote, with enough people you can detect a fruit fly. It's a great quote, right? It's true. So under the circumstance, if you have a statistical significance, but a very tiny effect size, that is usually because you have a ginormous sample size. Make sense? So how do we increase power? Well, you can change your alpha level. You can use a homogeneous sample. More importantly, you can decrease the spread, right, of your sample. You can up your sample size, or you can increase your dosage, as in you're not increasing your effect in the population, you're increasing your effect size that you're able to get in your sample by increasing the dosage, right? You're not changing whether or not Advil works. You're giving them some more, right? To show that, think about what power is, right? Power is the ability to detect an effect that is actually there. The other way to think about it is be able to illuminate an effect that is actually there. So Advil works by giving Advil more Advil, I can see that it works. And that's power, right? Being able to actually detect that it works, not just that it works. Now, changing alpha is pretty easy. Why does it increase power? Well, if this is alpha of 0.01, here's my power region, right? If I have a value here, let's assume there's an effect for a second. I didn't find it, right? I'm retaining the null. If I move my alpha to 0.05, now I found it, right? But what's the problem here? I increased the probability of type 1 error. Okay? So can you do that? Sure. Would I advise it? Depends on, someone asked me what's worse, type 1 error, type 2 error. Totally depends, right? And you can make an argument for either, depending on what it is.
He claims.
Increasing power, a priori option number 2. Actually, this is one option. Think test statistic. What is a test statistic a ratio of? Effect and error. And what do we use this test statistic for? And specifically, we use that test statistic to make a decision about rejecting or retaining the null, right? So statistical significance, which is required for power, depends on where we're putting that test statistic, right? It depends on whether we're putting it here, right? Or here, yes? So a T here or a T here. Well, if our test statistic is a ratio of effect to error, it should follow pretty logically that the higher our test statistic is, the way further out it is, right? That's going to make us more to reject the null hypothesis, which is a part of power, right? So we could either make the numerator bigger, meaning more effect. We'll get to that in a second. That's the dosage part, right? Or we can reduce the what, right? So this is really the reason I put 2 and 3 together is because this is really both about reducing error, right? I don't get calls all day, but I get 12. Okay, right? So to reduce error, there's 2 ways to do that, right? Easy way, up your sample size, right? Less easy way, remember we looked at that your friends rate the restaurant example. If the ratings are all over the place, meaning your sample is really, really spread, you have more error, right? So use a more homogeneous sample. Sushi. That's a good example. People who sushi more, right? Go ahead.
You said that we're calculating power, we assume an effect. So what factors?
Past literature. So think about the Cohen's d. The only thing we've looked at is Cohen's d, right? So we've seen 0.2 is small, 0.5-ish, 0.4 to 0.5 is moderate, and anything above 0.8 would be large. Generally, you would look, let's say, at the phenomenon you're interested in, and let's say you're seeing effect sizes in the range of probably 0.2s, given psychology and evaluation. right? I probably wouldn't use 0.2. I'd probably aim slightly more conservatively, right? Maybe 0.1, maybe 0.15. Generally 0.15, 0.2 is decent. So you usually want to aim a little bit lower than the effect you would actually expect, right? Because you'd rather underestimate that effect size than overestimate, because then you won't capture it. Some people give rules for how to do that. You should always just do this for psychology. I have to look and see what are for the phenomenon I'm studying, what is the general effect size we usually get. So decrease variance, increase sample size. And then the last one is, right, if we think about the ratio, really what you're trying to do through number one is easy. That's move the criteria. You're really only doing two big picture things. You're either moving the criteria or you're moving the calculated value, right? The criteria, the only way to move the criteria is move the alpha. How can you move the calculated value? Well, you can make the numerator bigger or the denominator smaller. To make the denominator smaller, you can up the sample size or decrease the variance. And to make the numerator bigger, you can make that sample mean further away, right? For example, here's another example. Let's say the average person in the United States takes, 30 minutes to fall asleep at night, right? You're testing a new version of melatonin. So you give somebody a quarter of a melatonin gummy, right? And nothing happens. So what you do is you compare the sample mean of the people you gave the melatonin gummy to this average of 30, and you don't find a difference. Therefore, even if there is one underneath the hood, you haven't detected it. Well, what do? Move that difference further away. Give them a whole gummy, right? They're out in 5 minutes, right? That's dosage, effect size via dosage. And that's literally everything you've learned in stats. Literally stats. Oh, what do I have in here? This is just extra stuff. You can't ever know truth. We know, so what do we have in our toolkit? So we use, last thing, putting it all together. So we do all that, and then we have all this information that we use collectively to make the best inference we can back to the population, right? We have a stats toolkit that right now has 3 things in it, and then we're going to add another one in to our inference toolkit after the exam. So right now, right, we have significance. So when we're trying to evaluate if something is going on in the population, we have this binary yes, no, right? We also have directionality. Is this sample mean higher or lower than the status quo? And we have effect size. So we have how far apart is our sample from the population or the status quo. And then afterwards, we're gonna talk about confidence and uncertainty after the exam. This is fun for you. We're not doing this in class. This is a study fun tool for you. Someone was like, can we practice comparing and contrasting concepts again? I appreciate the probability